Hello, in this video we are talking about section 6.2, specifically trigonometric substitution as an integration technique in section 6.2. We're considering the integral of the square root of a squared minus x squared dx. Now this is the sort of integral that would arise if we're trying to find the area of a circle, so it is something that comes up in some applications. But we need to know how to integrate it because currently all of the integration techniques we've talked about do not work here. A U substitution doesn't work because of the fact that we don't have anything outside of the integral. So there has to be something else that we can use. What we're going to use in this case is what's called a trig substitution. So let's see what would happen if we used the substitution x is equal to a sine theta. Well, just like with a U substitution, if we pick some sort of substitution, x equals a sine theta, then we need to figure out what the derivative is first. So that would make dx equal to a cosine theta d theta. Now the difference between this sort of substitution and a U substitution is we don't need to rearrange. We are just going to substitute in. So what I mean by that is if we have the integral of the square root of a squared minus x squared dx, a is a constant, so that stays the same. X is a sine theta, so all of that gets squared, and then dx is a cosine theta d theta. Well, the problem with this is currently this looks like it's more complicated than what we started with. So what's the benefit of doing a substitution like what we chose? Well, to see the benefit, we need to simplify. So first off, squaring the a sine theta, we're going to get a squared minus a squared sine squared theta. We will have an a cosine of theta outside of the square root, and then of course our d theta. Now notice that both of our terms under the square root have an a squared, so let's go ahead and factor that out. A squared times 1 minus sine squared theta. We can't forget our a cosine theta d theta. And notice that 1 minus sine squared is something that should look familiar to you because of the Pythagorean identity involving sine and cosine. This ends up equaling cosine squared of theta. So what that means then is we have the integral of the square root of a squared times cosine squared theta, a cosine theta d theta. So now we can rewrite the square root, since it's a product of terms, as the square root of a squared times the square root of cosine squared theta, which both simplify to a and cosine theta. So we end up with the integral of a cosine theta times a cosine theta d theta. Our a's are constants. We can pull that out, so we get a squared integral of cosine squared theta d theta, and this is something that we can integrate because it's a trig integral, which is what we just finished talking about. Specifically in this case, you would use the half angle identity cosine squared theta is equal to 1 plus cosine of 2 theta over 2. But from here out, you can finish this on your own. Well, almost. There's a few more details that we need to talk about before you can quite finish this on your own, because of the fact that we still need to talk about how to rewrite the final answer in terms of x. Because if you recall with a u substitution, you always need to rewrite your final answer back in terms of whatever your original variable is with an indefinite integral. Same thing is true of trig substitution. So we will get to that later in this section, but this is as far as we're going to go here for now.